In this set of videos, we will talk about balancing redox reactions by their half reactions. As the name half reaction implies, it is only half of the overall reactions. Now remember, in a redox reaction, one species must be oxidized and one must be reduced. Well, if I have any metallic atom to become an ion, it has to lose electrons or be oxidized. On the other hand, if a metallic ion is to become a metal, a solid metal, it has to gain electrons or becomes reduced. So let's look at some specific examples. We have solid zinc. Solid zinc, being neutral, has an oxidation number of 0, becoming zinc 2+ ion. 2+ ion, so the oxidation number for zinc 2+ is +2. How did it happen? Go from 0 to +2. It has to give up 2 electrons as well. On the other hand, for copper 2+ ions, it is 2+, the oxidation number, +2. It gains 2 electrons to become neutral copper metal. And being a neutral atom, copper has an oxidation number of 0. So here we've just written 2 reactions, each of which is separate. One, we have the oxidation of zinc and the reduction of copper ion. These are known as half reactions. But however, when you combine them together, you have a full redox reaction. Why do we write a half reaction? It is a very clear way to show either a loss or a gain of electron for any one particular chemical species. So again, let's look at the copper and zinc reaction. If we are given the full reaction, net ionic reaction of zinc solid plus copper ion yields solids copper and zinc ion, well, what happens to the zinc metal? Well, it went from a solid into an ion, and it went from an oxidation number of 0 to +2. Its oxidation number increased, therefore it must have been oxidized. On the other hand, for copper, it went from oxidation number of +2 to 0. It went from an ion into a solid. It must have been reduced. We can actually write the electrons as either a product or a reactant in our half reactions. If the electron is a product, we know the chemical species is being oxidized. However, if the electron is a reactant, we can write that we can know that the chemical species, copper ion in this case, is being reduced. As a quick reminder on the definition of oxidation and reduction, remember, species that loses electron is being oxidized. However, it's called the reduction agent. Remember, in the previous past we said oxidation is loss or oil. Well, now we can also say LEO, loss of electron, is oxidation. On the other hand, if we have species that gains electrons, is now said to be reduced, same thing as before. It's now the oxidizing agent. This mnemonic in the past was RIG, R-I-G, reduction is gain. Now we have another mnemonic, GER, gain of electron is being reduced. And Leo goes with GER because Leo, the lion, here's a lion, says GER. So now we have 2 mnemonics to help us remember the definition of oxidation and reduction. Either oil rig or Leo the lion says GER. So let's go through an example of where we're asked to find the oxidation and reduction half reactions. Our example here is a piece of lead is being corroded by a solution of silver nitrate. The first thing we're going to do is to write the non-ionic equations, just like we did in Chem 20. So we have solid lead plus 2 silver nitrates yields 2 solid silver and lead 2 nitrate solution. Next step, we'd write a total ionic equation. So we have to ionize silver nitrate into silver ion and nitrate ion. And because silver nitrate is soluble, we also ionize it into lead 2+ ion and nitrate ion. Next, we cancel out the spectator ions. In this case is the 2 nitrate ions. So then at the end of the day, we have our net ionic equation. Lead solid plus 2 silver ions yield 2 silver and lead ions. If we look at our net equation, we can see that solid lead is being oxidized into lead ions, whereas silver ions is being reduced into solid silver. And on the next slide, we'll write half reactions for those equations. So here we have silver solid being oxidized into lead 2+. Well, in order to balance up the charges, we have to add 2 negative things on the product side, or in this case 2 electrons. For the reduction reaction, we have 2 silver ions converted into neutral silver atoms. And again, to keep the charges balanced, we need to add 2 electrons to our reactant side because it's a reduction reaction. Because all the coefficients here are 2, here and here and here, we can actually reduce it into a simpler form of just plain silver ions plus an electron yield solid silver. Here the oxidation agent is the species that gains the electrons, in this case is silver ions, and our reduction agent is the species that loses electrons, that gets oxidized itself, in this case it is the solid lead. So as you can see, it's relatively straightforward to write the oxidation half reaction and the reduction half reaction from any given equation. One of the more important parts is to remember to reduce any big numbers into small numbers as possible. In this case, we could reduce the 2's into the invisible 1's. Let's look at a slightly more complex example. Here we have chlorine is being converted to perchlorate ion in an acidic solution. We're asked to find a half reaction and determine if it's a reduction half reaction or an oxidation reaction. Now the steps we're going to follow, it's actually quite similar to balancing redox reactions by oxidation numbers. Remember, the first part is to balance all the atoms except for O's and H's. So let's start. So we have Cl2 becoming perchlorate. Notice we have 2 chlorines on the left and only 1 on the right. Therefore, we need a coefficient of 2 on the perchlorate. Now that we've balanced the Cl's, let's balance the O's. And to do so, we're going to add water to either the reactant side or the product side. Initially, we have 2 molecules of perchlorate, and each molecule of perchlorate has 4 oxygens, so we have 8 oxygens on the right. Therefore, to balance out the 8 oxygens on the right, we're going to need to add 8 waters on the left to balance out the O's. The next, we're going to balance out the hydrogens. By adding the 8 waters, we added 16 atoms of hydrogen. To balance that out, we're going to need to add 16 H pluses on our product side. When we're balancing by oxidation number, we double check the charges are balanced. In this case, we're going to balance the charges by adding electrons to either side. And if we look at the charges, we have a total of charges of -2 on the left and 16 positive for a total charge of 14 positive. Whereas on the right-hand side, or left-hand side, sorry, the net charge is 0. Therefore, to balance out the 14 positive charges, we're going to need to add 14 electrons on the right. And notice we now have electrons as a product. Therefore, we know this is going to be an oxidation reaction. Chlorine is going to lose electrons to the environment. The last step is to cancel out anything on the same side. So if you have any water or electrons that are on both the product and the reactant side. In this case, there aren't any. Therefore, we're now done with balancing the equation. We're done with determining the oxidation half reaction. Okay, now that we've done a half reaction in an acidic medium, let's now do one for a basic medium. So here we have aqueous permanganate. Ions are converted, or we tell you now it's reduced to solid manganese oxide. And then we're asked to find a half reaction and to determine if it's reduction or a oxidation. We're going to follow the same steps for the first 5 parts, but then we're going to add 2 steps to it towards the end. So first we have permanganate, MnO4, being converted to MnO2. The first thing we're going to do is balance the Mn, and as it is right now, it's already balanced. We have 1 Mn on the left and 1 Mn on the right. Next thing we're going to do is balance the oxygens by adding water. Right now we have 4 oxygens on the left, 2 oxygens on the right. Therefore, we're going to need to add 2 waters on the right to balance out the O's. And then we're going to balance out the H's now. We have here 4 hydrogens on the right, sorry. So now on the left, we need to add in 4 H pluses. Next thing we're going to do is balance out the charges. We have positive 3 on the left and a 0 on the right. So therefore we're going to add 3 electrons on the left to balance out the charges. Because we're adding electrons to our reaction side, this is a reduction half reaction. And now if we're told that this is being done in an acidic medium, we're now done because we have the atoms balance and the charges balance. However, we're told this is in a basic medium, so just like balancing redox reactions by oxidation numbers in a basic medium, we now need to add hydroxides to the side with excess hydroniums, excess hydrogens, in order to create a basic medium. Because we have 4 H pluses on the left, we now need to add 4 hydroxides in order to balance them out. When we add 4 hydroxides to the left, we also need to add 4 hydroxides to the right. And now we can combine our hydroxides and hydrogens to create water. So now we have 4 waters. But now we notice that 2 of these waters can cancel out with 2 of the waters on the right hand side. So now it's no longer 4 waters on the left, it's just 2 waters on the left. The hydroxide is no longer there because we created water, and everything looks balanced. And this is again very similar to balancing by oxidation numbers. We can now combine our knowledge of oxidation half reactions and reduction half reactions to build a complete redox reaction. The example here, we have dichromate reacting with bromide ions to yield chromium 3+ ions and liquid bromine. By looking at the oxidation numbers, we can tell that dichromate will be reduced, whereas bromide is going to be oxidized. So then we go through our steps, and we go through our half reaction steps, and we find out the balanced reduction half reaction is this. So we have dichromate adding 14 hydrogens, so we know this is happening in an acidic medium, plus 6 electrons, again because this is a reduction reaction, the electrons are on the reactant side, to yield 2 chromium ions and 7 waters. Similarly, we can determine the oxidation half reaction, and that is 2 bromides yielding bromine liquid, or bromine gas, or liquid should be, plus 2 electrons. So those are our half reactions. Now we can put these 2 half reactions together to come up with a complete redox reaction. However, in a complete redox reaction, we cannot have excess electrons floating around, because for every electron that is oxidized, it has to be absorbed, it has to be gained by a metal somewhere. Now, if we look at our reduction half reaction, we see that there are 6 electrons involved, whereas in a oxidation half reaction, there are only 2 electrons involved. Therefore, we have to make a common multiple between 6 and 2 because we cannot have excess electrons left over from our reaction. So therefore, the lowest common multiple between 2 and 6 is 6. That means that in our oxidation reaction, we have to give up a total of 6 electrons, and in our reduction reaction, we have to gain a total of 6 electrons as well. The only way we can do that is to multiply our oxidation reaction by 3. So we have to multiply everything in our oxidation reaction by 3, so that at the end of the day, when you add everything together, we don't have 2 bromides anymore. We now have 6 bromides on our reactant side, and instead of having just the 1 bromine on the product side, we now have 3. Notice everything else is just added. If there are excess hydrogens or extra waters on each side, we can cancel them out too, and those are some practices that you can do in the practice booklet.